So first I will go quickly through the last part of last lecture about representations in general and the autoencoders. So that is a specific architecture in deep learning. And then I will go through some of the ideas related to how to represent molecules and materials in when we apply machine learning to the problems in chemistry and material science. So the general idea was that say a neural network at each layer will have a transformation, so a combination of an affine transformation and then a nonlinear activation of the initial input, right? So the initial input would be any kind of description or descriptor of the system or the kind of the data that we have at hand, and then if you look into any layer of a neural network, you can understand the values that one has as output of the neurons at each layer as a representation of the input, right? So that say if one is doing a classification, and since the last layer in a classifier is doing a linear classification, it follows that say if your task is a binary classification, the representation has to change from any kind of complex representation in the input to a linear kind of so a representation such that you can do a linear split of the data, right? So everything that it is on one side of a dividing hyperplane is yes, and the rest is no. And so this observation gives the idea that one can also play around with the learned representation. So the network is by all means learning a representation, and say, okay, the moment I have this final representation before the linear classification, or in any case before I do the final prediction, I could sample, I could pick any point in, say, in the region where I have the classification I like, and if I am able to invert it, I can go back to the initial data points, right? So, and then we can design a network that does that explicitly. So we go to a representation through a multi-layer perceptor in the network, and then we, through another network, we go back to the initial representation. And so the network on the left is called encoder, and the other one is called decoder. And I also mentioned that if you had a linear only network, this operation would find nothing else that the principal component analysis up to the dimensionality, that is the number of nodes that you have in the latest space, right? So principal component analysis, you have all the eigenvectors, and then you select how many you want to keep. While if you do this, you would be forced to have the dimensionality that you have given by the number of nodes in the inner layer. And the next step was to say, okay, well, first of all, if I introduce nonlinearities, I can capture nonlinearities, right? So instead of just having a principal component analysis that is intrinsically linear, I could kind of map any complex surface, hypersurface where the data live into the low-dimensional representation, where the idea is that, so in this case, we are going from initial representation that is two-dimensional to a kind of one-dimensional internal representation, and the catch is that everything that departs from being exactly one-dimensional is treated as noise, right? So the network is learning to decouple the basically the projection onto this linear manifold that is part of the learning, decouple the projection from the perpendicular components that are treated as noise. So the autoencoder is reconstructing the input via this kind of bottleneck that it is imposed. Yeah, typically the dimensionality here is smaller than the dimensionality outside. You can also design an autoencoder with larger dimensionality, but that would make very little sense. The next step that leads to the variational autoencoder is the idea of saying, okay, I do not want to leave open to the network learning the kind of distribution the data have on the latent representation, right? So if you just do a loss function like this one, so that you just want to reconstruct the input, then there can be any distribution on the latent representation, so the internal representation, right? So if it was in this kind of manifold here, the data could be distributed in any way. So if you are trying to invert, so you would have the map to invert. So if you select a point here, you would be able to go back to the initial data points, but you do not know necessarily the distribution that you have. So basically, if you sample from, you don't know how to sample this unidimensional, this kind of representation, right? So it could be uniform, it could be anything. So the idea is to impose a specific shape of the distribution on the latent space. For many reasons, the typical choice is a Gaussian. It's a normal distribution, so Gaussian with the average equals 0 and standard deviation equal 1. The loss function is then kind of modified by including, first of all, of course, we want to minimize the reconstruction error, but also we want that the distribution on the latent space, Z, and the Gaussian that we have selected are as close as possible, and we do that via the Kullback-Leiber divergence, and we have a kind of weighting factor between the two requirement that they give to the loss function. So that is the typical regularized loss function. So that means that lambda is an hyperparameter, so we have to try different lambdas in order to see which one is working the best. So that's the story always with hyperparameters. It's rare that we can evaluate in other ways than just trying a set of them and see how they works. So, and I just mentioned that if since sometimes going from the initial distribution in the original space to the multidimensional, multivariate Gaussian in the latent space, it could be very difficult in training. So you can set up the problem, but often it is a difficult training. So people use chain of these autoencoders, so that you do stepwise this transformation from the initial distribution to the Gaussian, and this has the name of diffusion. So there are techniques for training that. So I didn't specify more than that, just to say that basically the variation autoencoder is the seminal idea behind generative AI. So the idea that we can basically start from a random selection of data points in a distribution, and when we have trained the decoder, we can go back to a possible data point, right? So the original application was pictures, so you just start from random noise distributed as it should in the latent space, and then you get a picture that we recognize as a meaningful picture because the network has been trained to distillate what is the manifold on which the meaningful for human picture look like, and so you can reconstruct them. Okay, so right, so let me go to the new stuff. So I started last time, but basically restart. So now we want to kind of say the properties of descriptors / representations, and after this I will try also to give a bit more systematic nomenclature, because sometimes you hear descriptor, feature, representation. I try to systematize a little bit this nomenclature, but first I start with the properties. Let's say for atoms, well, for molecules more than atoms, and materials in general. So, like the kind of property 0, kind of obvious, but worth specifying, like everything that is like the zeroth law of thermodynamics. It's kind of implicit, but it's better to say. So such descriptor should be defined for all the data in our population, right? So in general, a descriptor / representation would be a numerical encoding of whatever you have as a data point, right? So you've seen, you start from a picture, and you have all your convolutional layers, and then the outcome of the convolutional layers is a representation that goes into a multi-layer perceptron in order to classify the image, add a caption or whatever. In language models, your sentence, book, whatever, is mapped into a numerical representation, a vector, that goes as an input to your network, right? So sometimes we have a kind of network architecture itself to evaluate the descriptor. Sometimes we try to have something beforehand. So, but the idea is the same. In any case, is important that we can define for all the data points this descriptor. Otherwise, we may encounter data points that cannot be described, and so we cannot do inference on them. Very important now, more specific to molecules and materials, but not so specifically, is that the descriptor should encode, should be aware and be consistent with all the known invariances, right? So if we think about the system of atoms, we need, say, permutation of the atoms label, right? So if you say I have atoms 1, 2, 3, 4, the descriptor should not depend on the order I label the atoms, because we know that any property the system will not be dependent on this labeling. And then, of course, the obvious translation rotation, for example. And and anything else that we may know. Then there is one that is, so the general term could be smoothness. Could be expressed also in terms of similar data, data points have a similar descriptor. So this is so since we have a numerical representation, we want that in some sense, if two data points are similar with respect to the property that we want to make inference of, the descriptor is close by. Since now the descriptor is a vector, it's a numerical representation, it will be close by in vector sense, so like cosine distance or whatever, Euclidean distance will be close by. So the idea is that we perturb a little bit the input data. Also the descriptor should change just a little bit. So there should be some local stability in the mapping between the data and the descriptor. Of course, similar data points, I already mentioned, this is related to the property that we want to evaluate, right? So if we are doing some classification, we want that two data with the same classification, the data points, two materials, two molecules. If we are evaluating forces, it will be really the coordinate displacement of the atoms, that if you change a little bit, the forces will change only a little bit. Therefore, the representation should change a little bit, only a little bit. Okay, and then there is this statement, requirement of global uniqueness, which I put with a star because it has some, I mean, it has to be specified. So ideally, you want that, so each data point is mapped on a well-defined descriptor, so that in principle you can invert the map, right? So we have seen in the idea of autoencoders, right, that you want to invert. However, it depends on the problem, what you mean by global uniqueness. So let's say that you have, say molecules, and you are given, so your very input in your database are actually the coordinates of the atom, right? And you're predicting properties of the ground state of the molecule, right? So you want that if you are given slightly different coordinates, or say the distances of the bonds or whatever, because maybe the molecule has been measured or relaxed with different force fields or whatever, actually you're predicting the same properties, right? So if you are, so you don't want to be so sensitive to the local geometry. So there are situations in which you say, okay, actually what I'm predicting are the properties of the ground state for the whole attraction basin, so all the small distortion of that molecule. So this uniqueness depends on the problem. If you are evaluating forces, you want to be extremely sensitive, or energies, to the actual coordinates. But if you are evaluating a kind of ground state property, you don't want that your machine learning model tries to understand the slight difference between the possible different inputs that you give while you're still representing exactly the same molecule, and you want to evaluate the same. So this is why the global uniqueness has a star. It depends on the problem. Then I mentioned last time this kind of size invariance. So the idea is that now more specifically not more specifically, it is easy to understand for an atomistic system, so you want to train a model so that if you have given all your data with a supercell of 100 atoms, you can do predictions also on 1,000 atoms. Because typically is what you dream, that you train on a small system, and then the model can be applied to a much larger system, because now you have a faster model than your reference data, and so it would be really a pity if you are bound to the size, and indeed physically it doesn't really make sense that you cannot transfer to larger systems. More kind of subtle is the situation in which you, as I will show in a while, you actually represent materials as a whole by means of their chemical formulas or some derivative of the chemical formulas, and you want to treat materials with any given number of elements, so binary and ternaries. So you don't want that you may not want that your descriptor is good only for binaries, and then you don't have no idea what to do with the ternary material if you all of a sudden are there. So you have to design carefully at the very beginning if you want to have this flexibility. And then the kind of this is not a requirement, let's say, that is related to the mathematical model itself, is related to the meaningfulness of trying to learn the model, is related to the computational complexity. So whatever you do, your descriptor should be much, but at least a bit computationally less complex, less demanding than evaluating the properties by means of your reference model, right? So typical application, so you have your reference data that are calculated with density functional theory, and you want that the evaluation of the descriptor plus actually the model evaluation are less expensive, much less expensive than the DFT itself, right? And yeah, with modern neural networks, this is not so given. So you have to think sometimes what you're doing. So in any case, so the idea is that yeah, you need to evaluate a descriptor that it is let's say, yeah, computationally less significantly less demanding than evaluating the model itself. Okay, so these are the properties, and then basically I want to do a bit of a classification of possible descriptors. But first, I promised the nomenclature a bit. So. Oh, this is very bad. So in general, we could say that we are evaluating some property. Right, so we are doing inference on the property, and in the general case, this could depend on different models together. So one model could be one neural network, but you could have anything else, and sometimes you want to combine the models, right? So this is the idea of kind of ensemble modeling. Which you train models that you try to design so that they do independent mistakes, so that when you combine the information from different models, you get a better prediction, right? So the typical combination is to take an average if you're predicting a property, a numerical, a scalar property, or if your classification is a kind of vote by committee, so the majority wins, for example, and you have different models, and the selection that gets most votes is the one, and you can demonstrate. So when you have decision trees, you combine them properly in so-called random forests, you get a much more robust model. So you, in a random forest, you would have that your properties predicted combining the different decision trees. So the general case is that you can combine models. They can be very heterogeneous, this model. You can really train independently the models, and then they say, let's take the average or the vote by committee of them, and yeah, you can show that would reduce your prediction error if the errors are indeed uncorrelated. If the models have correlated errors, you don't gain very much, but it's difficult to kind of show actually, you just show empirically. So how do I do this? So the model is actually a function, and here it enters the representation. So this would be the input, the actual input to the model, right? So if you have a decision tree, would be the input to the decision tree. If you have a neural network, typically a representation would be, say, the last latent space representation before the last layer. So the network is learning a representation. Then this representation is a function of the descriptor. So the descriptor is the overall input. Yeah, here I could put dot dot because in principle you could use multiple representations as well as multiple descriptors, but let's just fix. So it would be your input. So in a decision tree, these two guys would be the same because your input description is what enters the model, and the model makes a prediction on the basis of the descriptor. In a neural network, the descriptor would be the input, x1, x2, x3, and representation would be the inner representation. And so the descriptor in general is a vector, and in general it could be thought as a collection of features. So the components of the descriptor would be features. Of course, this is not, as any nomenclature is not universal consensus. It's just the idea that there are different things. So you typically have ways to represent your input, and they could be heterogeneous, right? So it could be even that some features here are say binary or some kind of discrete set of features, and some are scalars, and you group them together to form a descriptor. So this is, so in computer science they call it vector, but it's not necessary to be a vector in physical meaning. So it doesn't have to have any invariance property or covariance properties. So it's just a collection. It is just a collection of different input information. And this makes the descriptor. The descriptor is then in some model classes transformed into representation, and then we go to the model, and connected the model, we go to the property. So this was an attempt to get another name that you find often in literature instead of descriptor is the fingerprint, especially when you are doing so-called material informatics that I come in a second to. So yeah, this is this attempt to distinguish. So in principle, features, descriptor, and representation are not the same thing. Some people may disagree on where to put it in a hierarchy, but there is definitely a hierarchy here of different concepts than they are named differently in different places. Okay. This given, let me try to classify. So now we are specifically in material science, in chemistry, material science, and we want to. So let me characterize the features. So we have two main branches. Features that come from the configuration, atomic configuration. And features that come from ensemble description. So the atomic configuration means that one way or another, one starts from a set of positions and atomic numbers to uniquely identify each atom. And then we, as I will show in a second, we want to go from this kind of how to say, obvious representation that would be enough, of course, to build our Hamiltonian, to a representation that has the proper invariances, because if you're doing physical modeling, typically your Hamiltonian will include the invariance. Typically, when we do machine learning, we may not want to have the model learn the invariances from scratch. So we do that by presenting the atomic configuration already in a permutational for the atoms of the same species, permutation invariance, translation, and rotation, and whatever other invariants that could be important, some mirror or whatever kind of invariance. Right, and when we go to the ensemble description, the kind of prototypical one is starting from the chemical formula. Right, so say that we represent a material as some kind of a chemical formula. So there will be element A, B, C, each with its stoichiometric index. And what we do to construct a descriptor that is usable for making inference, we may use summary statistics in this way. So let's say we have a bunch of materials or molecules for which so the only characterization that we have essentially is the chemical formula, the brute formula. We could have also the topological kind of expression that comes in different scenarios. But let's say we just have the chemical formula and we want to predict properties of molecules or materials given the chemical formula. And so one way we can represent numerically the material is just to say, okay, I know properties of the atoms A, B, and C for each atom I could have a set of properties. I could do calculations in the gas phase, measurement in the gas phase, or more subtly, each element would have a stable solid, well, almost, except hydrogen could be debated, but in any case, you define a kind of reference phase for each that is monatomic for each element in the periodic table, and then you say the property of that solid or whatever reference state are the property of the element, right? So to get out of abstraction, you say, okay, gas phase atoms, you would have, you can define, I don't know, some extension of sp orbitals that you can calculate, and you define what you take, the maximum of the density of that orbital. Obviously you can take the atomic number, but you may think easily that that is not the best, because some chemical elements that have nearby atomic number are not that similar, right? So if you go from the rare gas to the next halogen, you would have, to the next, whatever it's called, alkaline. They have the atomic number that differs by 1, but they have very different properties, right? So then you may want to have something different. So electronegativity, well, electronegativity is, you have to, so what is that? Ionization potential you can measure, and a few other properties. Then you could have, if you think about the reference state, you could have density of that reference state. If you assume that it is a solid, you could have melting point, melting temperature at reference pressure, and so on and so forth. So this is just a set of numbers that would characterize the element. The element, and the idea is that they establish a kind of similarity in the representation space, so that when you move from one material to the other, you go smoothly among these properties. So how the summary statistics works is kind of obvious. So for any properties, you just take for the material, for example, the average. So you would have so the feature F for the material would be the average. So you use the stoichiometric coefficient, and then you have the feature for the atom A plus the so and so on and so forth. Feature for B, and so on and so forth, or some kind of dispersion, right? So you could take, you treat the chemical formula as a distribution, and you say, so basically I have XA of atom A, XB of atom B, so any property is reweighted by these weights in the distribution. So I could have some kind of standard deviation, that would be then XA of FA minus F average square, and so on and so forth, right? So this would capture how much different is a certain property within your chemical formula. So and these are actually used a lot. And when we use this kind of descriptor, what we do is the so-called materials informatics. And I want to show you a few slides of examples of actual descriptors that have been used for materials informatics in publications. So I've selected because they are in some sense original, or let's say just to show how much creative you can be, right? So this first one is from one of the early work in the field, 2013, when community was just starting using more and more machine learning to predict materials and molecular properties. So the problem here is that they had periodic polymers that would be formed only of these possible 7 blocks. And then what the authors here chose for descriptor was just counting. So you get this polymer, and then you count how many times. So you have an histogram of how many times each of the 7 building blocks would appear, and then how many times you had neighbor pairs, and how many times you had triplets of the same block, right? It's just an histogram where it counts for each block, how many you have for each II pair, how many you have, and for each triplet. So it's 20 because, yeah, basically the number of building block 1 is defined by the others. So you have 21 dimensions minus 1 because 1 is redundant. So you have basically a 20-dimensional array of numbers, and each of them essentially represent uniquely any possible polymer that you have there. I mean, that it is unique, it is not given, because in principle you should give all the possible n-tuples in order to uniquely specify. But it was found empirically that this description was enough to. So materials that had essentially the same descriptor at the end would have exactly the same property. So they would be so similar that they had the same property. And here is just a parity plot, set of parity plot where they use exactly the same descriptor for predicting atomization energy, lattice parameter, electron affinity, blah blah, of this polymer. So all these are measure properties of these polymers, and they were able to predict. So this is a kind of it was a trial and error. So they started having just the histogram, it was not enough, and then they added the pairs and so on and so forth. So this was one example. This one is very creative. So from the group of Stefano Curtarolo, that also is a kind of early-ish paper, 2015. So they wanted to predict. Oh, sorry, the top here is wrong. Sorry, it remained from the previous slide. Forget about the top. So they wanted to predict properties of a set of bulk materials. And the modeling that they wanted to do was actually predict whether you had so actually the critical temperature to become superconductor. And they said, so this is obviously an involved property, and they fancied that it would depend on the band structure, and what it is creative is the way they encoded the band structure. Basically, they kind of histogrammed the band structure. So what you see here is the kind of fully defined DFT band structure, and then they said, okay, this is a density of state, the projection here, and then they kind of digitized the density of state. So what you see here is for each symmetry point, there was an histogram that you see is very coarse grain, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, they say 32. Okay, whatever. Few kind of bins for each symmetry point plus a discretization of the density of state. So, and basically they used these kind of strings concatenated to train a model to make prediction that was actually, at least in terms of classification, pretty useful, right? So so materials that had somewhat larger critical point with respect to lower, they were correctly classified. So this is kind of an example of something a bit creative. Here, much more recent, well, not much more, a bit more recent, 2017, time flies. So here they had, I forgot which class of material. I think these are perovskites, and they had different combinations of this. So the thing is that they used for each atom, atomic number, electronegativity, the most common oxidation state, and other properties that are properties that you read in a lookup table for each atom in the periodic table. So you have tabulated them for all, and then you combine them with this say summary statistics that I mentioned, and then they train a random forest to make prediction on here it was the lattice constant, if I remember correctly, and the band gap for sure. Yeah, this was the paper. Yeah. So, and they just represented, given the chemical formula, they represented the materials in that way. So where does one find these atomic properties? So there is a platform called MathMiner that has both the database as also Python scripts to evaluate those average, so those combined ensemble properties. I mean, there could be more. You could take the maximum or some kind of smooth maximum, some kind of soft max or whatever, and then so you have scripts there. And so the general idea is that you go from this kind of materials database to doing the so-called feature extraction. So you put together the extractions, and you have the machine learning tools and so on. So MathMiner is kind of full-fledged platform where you can do some simple, I would say, prediction. The power there is in creating the features. Then if you want to train a more complex model, of course, you most likely you don't stay within the MathMiner platform itself. You evaluate the features, and then you go to some more powerful capabilities. But it is worth knowing that essentially any kind of possible descriptor for materials informatics that you want to start with will be documented, and it is findable in this MathMiner library. Okay, so here then I jump to descriptors that are actually found by machine learning. So this now comes to my own work. So in this particular example, we had the task to predict the selectivity of a class of materials with respect, so that would act as a catalyst for a certain organic reaction. And so we collected a lot of features that some of them are listed here. Say these were done by measuring properties of these materials. So the idea is that the material was present, and it could be characterized by experiment, but measuring the selectivity is a more involved experiment. So the idea is that with somewhat simple characterization, we can predict a bit more complex properties. And so you have here, say, very heterogeneous properties, like some of them are kind of mesoscopic, like the pore volume is the way these materials would self-arrange in 3 dimension. Some of them are electronic, and so on. And then a method that I will mention, I will explain in a couple of weeks, not only selected, so there was a much larger set of possible input features, and the method selected only some of them, but also found a kind of possible expression how to combine these features into one descriptor, right? So you see, you have the work function at the numerator, and then you have a few things at the denominator, and then you have also this pore, also the numerator, but squared. So the pore as a larger, a different influence on the descriptor, and therefore on the model than the other one. So the fact that it is this product of things will come more clear in a couple of weeks. But just to say that these materials in this class were characterized by this set of 5 descriptors. So each time you want to predict the selectivity of this material, you would just look if you have this information from any database, or you have to measure these properties in order to make the prediction. Another from my own work. So we were evaluating the thermal conductivity of a class of binary materials, and we had a descriptor. So the descriptor is here. These two components here that depends on say the molar volume of the material, the Debye temperature, so something related to the harmonic phonons, and some factor that is related to how anharmonic the potential energy surface is. So I show this because of the point about complexity of the descriptor. So you are given the chemical formula. That's not enough to predict thermal conductivity. You need to work a little bit some computation, and then even evaluating how much an harmonic is the potential near the minimum is much less complex than evaluating the thermal conductivity, which requires much longer simulation and essentially much longer simulations. And so here we have that the thermal conductivity could be nicely evaluated over, you see, several order of magnitudes actually. So we predict a logarithm of that by means of an expression with a descriptor that it is actually found, right? So the fact that this is a kind of analytical expression, so the whole model, the predictor model, is an analytical expression, is a model class, comes from a model class that we'll explain in a couple of weeks. So it could be a neural network, but it's just to show that we characterize materials with what we need, and then we have. Then I come back to this. So these are examples from literature. The other class here starts from the atomic configuration, and there is another kind of forking here. One is that it is a specific configuration, and the other one is about a representative configuration. So this is an extension of what I was trying to say before. So you may want to have a descriptor that depends exactly on the coordinates of your atoms in the system, because you want to evaluate essentially forces and other observables that are sensitive to the exact position of the atoms. Or you may want to model your molecular material in terms of, say, a ground state configuration. And so basically you want to have a descriptor that is not so sensitive to the actual coordinates. At the same time, you may not want to say, okay, I give you the coordinates first, you relax the structure, and then you get your descriptor to get the prediction on the ground state. Because sometimes, essentially, after you have relaxed the structure, you have most of the properties that you may be interested in from your modeling. So, a notable example of this representative configuration is the topology kind of representation. So basically you map your coordinates into some kind of graph, and you just use the connectivity among the atoms as an input. Of course, giving a graph as an input is not straightforward. We have seen last time that if you want kind of the full-fledged properties of the graph, you need specific graph networks. but you can also play some tricks and evaluate some invariances of the topological graph. And an example is also in the next slide here. So this is this was from actually a competition that at some point we organized when I was in Berlin, where people had given coordinates of a class of material containing, as you see, indium gallium, so these indium gallium oxides, and in several crystal phases, and they had to evaluate properties of the crystals. And the guy that won the competition used something that is called the n-gram for crystals. So he invented n-grams for crystals. So n-grams is a concept that comes from natural language processing, and it is related to so you have tokens or words, and you histogram how many times you see a certain words, how many times you see a certain pair of words, certain triplets of words, and so on and so forth. So similar to this polymer example that I showed before. So the strategy here was that first of all, from the coordinates and just by looking at so some cutoff distance, the algorithm invented by this Yamamoto mapped the crystal structure into a graph. So the gallium atom would have a certain number of oxygen neighbors, and then it would kind of summarize the graph by means of a histogram, right? So how many times, so first of all, it identifies different species if they have 4 neighbors, 3 neighbors, or 5 neighbors, and so on. So you have aluminum 4, aluminum 5, aluminum 6, gallium 4, gallium 5, gallium 6. And so the n-gram is, so the 1 gram is just the histogram of how many times you see each of these species. So it's not just the atom, it's the atom and it's how many neighbors it has. It has already defined more features. And then the 2 gram would be how many times you see a certain number of pairs and so on. So, and these histograms here, 1 gram, 2 gram, I think he had 2 models, 1 gram and 2 grams, and one up to 3 grams. And the improvement between the up to 2 and up to 3 grams was so small that he basically kept the 2 gram, and it was able to, or probably it was the 3 gram was the winner, but the 2 gram was kind of very close. It would not have been the winner if it was only the 2 gram. Yeah, so that's the idea. And so you have, and again, so just think that you have this histogram here and also the one for the 2 gram. So they have all the nice properties, right? So it doesn't depend on the order you label the atom. It doesn't depend on, for sure, rotation and translation. It is smooth, because if you change a bit the coordinates, sometimes it doesn't even change. And then you go from one to another by just changing a little bit these intensities of the beams. And so you have all the properties in one descriptor. I mean, he didn't invent the n-grams, but the clever idea was how to map coordinates into these graphs and then read the graphs for relatively simple machine learning models. There were not so many data points. In general, it was trained on a couple of thousands of data points. So if you just started to do heavy graph neural network, it would not have worked. There were not enough data points to get something out of that. And this is also a consideration that one has always to think about. So on everything that we have seen in the last few lectures, so the transformers and the graph neural networks are essentially, and you can combine transformers and graph neural network, the most powerful tool that we have today in machine learning. They need a lot of data, so they are so much complexity that you really need hundreds of thousands, millions of data points. So it is unlikely that we will have this kind of data availability in material science. So we have to think a bit more on models that have that are much more parsimonious with the number of data. Okay, back. Now we go to the actual, say, descriptors that people have been inventing for describing one specific configuration. The idea is that you start from your coordinates that have the problem, of course, of that you have to decide an order, and they are not translational, rotational, invariant. And then you want to present your structure in a way that it is permutation, rotational, and translational invariant. And this is the input to your model. That at the beginning meaning, say, we go back now to the first one is Baylor-Parinello. Baylor-Parinello in 2007, and then the next one is from 2008. So this is the kind of the beginning of the era of machine learning for predicting property of specific configurations. And so there was debate whether one should use a neural network or other model classes like kernel methods, kernel ridge regression, Gaussian processes, this kind of thing. Later on, it was clearly demonstrated that it doesn't really matter. All the burden is on the descriptor. So then you design a little bit your model class, and it basically yields very similar results. Okay, so okay, I think I have to speed up here. Okay, so this is it. So the proposal for from Baylor and Parinello in 2007 was to represent atomic, say, environments, right? So rather than focusing on a descriptor for the whole structures, it became so the big idea was to say, okay, let me represent an atomic environment. So I have an atom I with some neighbors J, right? In any configurations, and I want essentially to present each of these configuration to my learning mechanism, and the idea here was to okay, represent first of all something that depends only on distances. So we have a radially decaying function, exponential of minus something, depends on the distance between I and J. And let me put, all these are parameters. And then there is a cutoff function. So this C is a cutoff that counts 1 when the atoms are closer to a certain distance, and so there is a kind of a parameter also here for the cutoff. And the point here is that these parameters in the descriptor are hyperparameters that have to be set, right? So basically, you don't know beforehand how are this value. You just start from some guess, and then you train your model, and then you go back and try to change these parameters. Your descriptor would be, so basically for each atom I, you would have a number here that is basically a kind of summary of the distances of the neighbors, where they are. I mean, this is a vector, right? So it's a, sorry, I should have made, this is a function, and it is presented as a vector. This is a function of R. So for each atom, you have this kind of sort of radial distribution function, and then there is something depending on angles, a bit more complicated, but it depends on the angle between the two, and then there is also something again depending on the distances, and then there is product of three cutoff, so that just says, okay, if the triplet is, they see each other or not. So basically, in this work of 2007 and essentially all the following work by Jörg Behler up to today, it would represent the atomic environments with these two set of functions, right? So one for each atom in the system. And this is just to say, okay, so we go, so check, so it is not super apparent. The permutation invariance with respect to the neighbors is clear because you sum here, so you lose the order. You are rotational invariant, so rotational here, well also here, it depends on the distances and so on. So these are fully fledged descriptor for this. Okay, these are called atomic. I should write it down. Atomic centered symmetry function. Okay, before I go to a possible criticism, let me introduce the second one. So this one is from Bartok. Condor. Xani in 2010. So when they said, let's, for each atomic environment, I can define, so first of all I go from atoms to Gaussians. So for each atom I plunk a Gaussian with a given width, and I represent the density of the system, so of the environment around an atom, as the sum over these Gaussians, right? So basically I say instead of this the collection of atoms, I have a collection of Gaussians centered on these atoms, and then it's just algebra. Then they say, okay, I can always express this sum of Gaussian as an expansion over a combined radial and angular basis function. So this G of R, well, it's not power. It's just so a function, a radial function, and then spherical harmonics. So product of this, and then I have some coefficients. So basically I do the expansion. I know this, so I have my position of the atoms. I can write down this density, and then I can project it on this given basis, and then I learn this coefficient, right? Well, not in the sense of machine learning. I find this coefficient for any given configuration of atoms. And then I construct, so this is not yet rotational invariant. I construct this object here. This is called the power spectrum of the density representation. So you basically sum over the M index, so the one in the spherical harmonics, and then you construct these power spectra that are invariant to translation, rotation, and so on. So these are objects. So you have the n and prime numbers, so coming from the from how many spherical, how many radial function you use for describing your distribution, and the angular, so the channel of the spherical harmonics. And then when you have this object here, you can construct models, right? So you can take, for example, the scalar product of two of these power spectra centered on two different atoms, and evaluate how similar are two environments. So basically you say, okay, if I have something that looks like this and something that looks like this, how close they are to each other, and basically by using this descriptor here, you can establish this. So the differences between the two environments will be how different they are locally, nothing to do with the translation and the rotation, right? Or the order you enumerate the atom. So involved, but the idea is that we go from, always remember that we are going from a collection of distances and species into this. And the last one, because I mean there are so many, but basically this one is the jackpot, because it can be demonstrated that it is the complete one. All the other ones are kind of so this is called atomic cluster expansion, introduced by Ralph Drautz in 2019. I need another token somewhere here. Okay, so the answer is very similar to at the beginning with the oh, I didn't say this is smooth overlap of atomic positions. So it starts with the expansion of the local density here as delta functions. So it was felt that there was no need to do this smearing of the positions, and then one can always introduce a one body basis. So again, the radial part and the spherical harmonic. So you have these functions here. They would represent environment, like so each atom with each neighbor, right? So the I is in the center and the J is in the neighborhood. And then one can construct atomic environment kind of basis functions by basically summing over this one body basis functions. So your environment would be the sum over all the neighbors of these functions that one has defined here. So this is a basis set that it is you can define it as complete. And then you can take so you can evaluate these coefficients by projecting onto the basis functions. So here would be permutational invariant, and then you do these products. The crucial step introduced by Drautz, not necessarily invented by him, but for this specific scenario of atomic environments, he said, okay, now let's take these products of all these basis function, and we truncate it at some body order. So these functions are one body. So each product of so two of them is the two body term, and three of them is a three body, and so on and so forth. So if you have an expansion like this one for one environment, and you take the product with another environment, you would have okay, the one body terms, but also the two body terms. And if you had a new one, you would have also the three body and four body, and so on and so forth. But then you can group the products by the body order, and you just take the first few. So you truncate here. So absolutely not trivial. The two-body term is exactly the same as this one, give or take the fact that here there is a sigma or in the so a Gaussian, and while here there is no Gaussian, but it's essentially the same. But in this way, Draughts has defined a systematic way to include all n bodies in your expansion. And then this is not yet rotational invariant. You have to take the integral over the the spherical angles of this. This gives this b, and this is our final descriptor. So you don't have to do this integral. There are some tabulated coefficient called the Klebsch-Gordon coefficients that for this kind of basis function are completely known. It's like on a book, it's like a few hundred pages book, but of course it is a library. So the good thing is that all these operations are relatively fast, because I mean everything is tabulated, and okay, of course Draughts and many other have codes for doing that. At the end of the day, you get these descriptors. Now these descriptors were so informative that the original application from Draughts was that the property of our system, for example energy, could be modeled just as a linear combination of the BZ. So the descriptor was so powerful in describing the local environment and distinguishing among different environments and so on, that if you just take a linear regression on this set of coefficients here, it could show that it could evaluate to any precision, any accuracy, the properties like energy or other properties of the system. So basically, it was even without machine learning. Or I mean, if you call linear regression machine learning, but yeah, in principle one should. But okay. Now, to close, I want to show also. So these was just about the descriptors. What about the kind of models that the classes that we use? So let me show. I wanted to show this. Getting slow. Okay. So what about potentials? Sometimes it's just a bit better. Okay. Potentials. And I wanted to show two examples of traditional potentials, just to see the difference between these and the machine learning ones, right? So this is the amber kind of potential. So very successful for organic up to biomolecules. And the idea here is that so we represent our molecule by a set of distances, by defining bonds and angles between bonds, torsional component, and then the non-bonded components, right? So, and then there is an harmonic potential with respect to the bond. So you say, okay, for each particular species, there is stiffness parameter and optimal distance, and then you evaluate the potential as a departure from that distance, the optimal angle, departure from that angle, torsion, some function, and the non-bonded say, okay, whatever pairs of atoms that was not bonded would have a kind of dispersion part and the Coulomb part. And here you have a lot of parameters, right? So for each species, so for each type of bond, you have to define this parameter 1 and 2. For each, again, triplet of, so pairs of bonds, you have to define this stiffness and the optimal angle, and the same for the torsions. So there were tens, there are still tens, if not a few hundreds parameters, depending on what system you have. And you needed a way to infer the topology, right? Again, to say, okay, what was bonding, what was not bonding, and so on. A kind of different class of classical potentials is the kind of bond order. Also known to be reactive potential. So the big drawback of force fields like or potentials like amber is that you cannot change topology. So you not only you have to infer it, but there is no description of a bond breaking, because this would be always stay harmonic, and there is no description on what happens. So a potential like so the first one of success was introduced by Tersov for silicon, and you have a repulsive part and attractive part, and the attractive part is modulated by the so-called bond order. So something that depends on the environment. And like for silicon, for example, it worked like this. So you had that the potential, so I had this repulsive part here and the attractive part here, so some exponentials, and the bond order part depended eventually on the angles. I mean, it's a bit hierarchical here, but the G is here, Gij, and this theta is inside here, and you had a potential that depends again on angle and distances, but it would be able to dynamically say accommodate. So you have I don't know 3 neighbors, and you have a 4th neighbor, and the approach of the 4th neighbor would have a smooth surface that accounts for like a sp2 to sp3 kind of hybridization, for example. That was basically the main point of this potential. Yeah, so this was just to give an idea. So you have a lot of parameters that are highly non-trivial to tune because they are all non-linear, you see. So like these C, D, lambdas are all parameters of the potential that comes from the data. So in some sense, also here, of course, everything was coming from the reference data. This potential were learned. The functional form had some idea behind, right? I mean, here there was a simple ansatz on the bonding interactions, but we could use the dispersion like this or the Coulomb like this because we have a model for Coulomb and dispersion, and so on and so forth. So this is just to give the general idea of potential before the machine learning. With machine learning, we start from a database, and there are 2 crucial things that comes from the database. One is the data location, so which data are actually there, where they are distributed, and the labels, so that we use for the training. Right? So we have 2 different challenges. We need labels that are accurate enough with respect to what we want to model, but also we need the data that are distributed in a meaningful way and not just in a non-significative way. And typically we then go to so a potential energy, so surface. So we have a representation in terms of coordinates, and then we have the any kind of rough surface as a function of the coordinate, and we go to a descriptor kind of representation that is typically a bit smoother, and then we go to a machine learning choice, model choice. And so the first machine learning model that was of great success was from the Baylor. Okay, I will comment here because if I transfer, I will may lose time. So the idea was to go from coordinates to this symmetric function representation, and then for each atom, your Baylor was training a dedicated machine learning, a dedicated multi-layer perceptron. So there was a neural network for each atom that was trained to give the energy, to give some energy, such that the sum of the energies is your reference energy total, right? So the problem was to connect all these networks such that same species, same parameters. So this is MLP-A, so the species A, the species B. It has one dedicated network each, but such that the update of the parameters is to all of them at the same time for all the data points. And then you combine them. And then the kind of more modern version in which it says, okay, this is good for short-range interactions. We cannot really capture the long range because these functions here have a cutoff. So basically, we cannot describe whatever happens outside the cutoff radius. So the influence from distant atom. And Baylor solved the problem by just decoupling into short and long. And the catch is that for the short range, it would still learn the energies with some neural network. And for the long range, same representation, but it learns the partial charges. So from the input, it just divides a charge partitioning scheme. It doesn't really matter to some extent that is not physical, provided that it is consistent. So with DFT, you use your Hirschfeld or whatever definition of charge partitioning. He would learn the charge partitioning, and then he plug into the Coulomb formula in order to get the energy, long energy, and then combine to get the total energy. It's a bit tricky to do the actual learning because you have to first evaluate the charges, subtract the long range, and train on the short range, but it is a fully defined algorithm. And this was just, say, one example. So the first example, the SOAP descriptor was used together with, say, kernel ridge regression, Gaussian process, so some kind of extended linear regression. And as I was saying, the ACE at the beginning was just a linear regression, and then it went into a graph network. A graph network, to be more precise, is a message passing network that gives rise to maze, where the M is all multi-message passing something ACE. So the idea is that this descriptor here, instead of being used for a linear regression, would go as initial representation in a graph network, and then we have this convolutional graph network machinery that we construct more complex representation. And then you say, so you trade a linear regression for a graph network? Yes, because you can use much lower order in the n-body expansion. So this linear regression, in order to get the accuracy, they would need to go to relatively large body order. When you plug the descriptor into a neural graph network, you can survive with much lower body order. So basically the other orders are what the network is trying to learn in a sparse way. So instead of having all the functions that it's just in the message passing machinery that learns what matters and what not. So overall, you get a simpler model still, if you include also the different chemical species. I didn't talk about very much how you go from one chemical species to the other. So basically you go to a large model that goes, so now exists, we have maze MP, the original one was MP0, MP is again message passing, and I mean, this is a model that one can access and use as it is. It is pretty intensive computationally, even after training. So it's extremely intensive, and so essentially all the information that were evaluated via DFT with more or less consistent setting were used to train this model from many different groups. So I want to close by saying that the most recent trend in our field, of course, coming from other fields. Oops. What? Okay, I should never move these things. Okay, I will rearrange before uploading. So we now talk about foundation model, fine-tuning, and distillation. So that is that you take a foundation model from the some library. It's called zero shot, so as it is, and then you use some reference data for the problem that you want, right? So here it is a particular performance for some system of water molecules. They took the maze model, and then they say, okay, then let's present a few configurations of these water molecules, and we fine-tune the same model. So that means that I further train my weights, but starting from the foundation model instead of from scratch. So I have a huge speed up on, a huge improvement on accuracy from 45-50 milliev per angstrom in the forces to less than 50. That is okay. But we have the same complexity. So the speed up here, you see relative speed is 1. So we have just a more accurate model, plus the fact that I had to fine tune it. So I spent some time. But now I train a much simpler model on top, using this model for producing data, right? Instead of using the reference model, DFT, that would be much more, more intensive. I use this model that I have fine-tuned in order to produce data to train a simpler model. For example, ACE with very few, so very small basis set. And so you see that if you get there, so you start from a corpus of data points, and you train your ACE model, you would get certain accuracy. But if you start using the model from that has already first been fine-tuned before, you would get a significantly more accurate model at the same speed. So basically, it is a way to train better light models, right? So the workflow is starting from a foundation, fine-tune it, use the fine-tuned foundation model as a data source for training a simpler model that would not generalize as good as the foundation model, but it will be very accurate. As you see, similar accuracy as the fine-tuned foundation model. Okay, that's it for machine learning interaction potential. Thank you.